Congestion and InfiniBand network, and will be presented by Malathi Veeraraghavan. So Malathi, in short, MV. So Malathi is a professor at the Charles L. Brown Department of Electrical and Computer Engineering at the University of Virginia. High-speed network research groups works is funded by the National Science Foundation and U.S. Department of Energy. She worked in the labs for 10 years before moving to academia.
Thank you very much. Hi everyone, I'm surprised to see as many of you here. Thank you for coming. So Fatma is my PhD student. Currently, Fabrice did all the measurements in this work, Fatma did the analysis, and John Dennis is my collaborator on this NSF project. So here's a quick outline. Since this is InfiniBand and most of the talks here are on good old internet, TCP/IP, I figured I'd give you a little background on InfiniBand. Can I just get a show of hands of how many of you know the InfiniBand protocol? Okay, a few, not too many. Okay, so bear with me while I go through the background, and so hopefully, so I'd love to get some feedback. One of the things I want to work on is a comparison of InfiniBand and Ethernet, TCP over Ethernet. IP sits in between. You'll see what I mean by that. If anybody is interested, I would love to collaborate. Okay, so InfiniBand, it turns out, it's always one step ahead of Ethernet in terms of rate. So it's like if we are at 100 gig with Ethernet, InfiniBand will be at 200, that sort of thing. So this particular machine that we used is called Yellowstone. It was at 56 gigabits per second when Ethernet was at 10. Okay. So low latency is really the goal, but what they've done is, in the protocol, it's link by link flow control. In other words, you don't send a packet till the other side says it has enough buffer space to accept the packet. And you think that's a good thing, right? That you're not going to have any packet losses, but actually it turns out it's a pretty lousy thing. It causes congestion to spread. And it's very interesting. The more you think about this, you start thinking about society at large and admission control and immigration and packet drops, and it's really weird. It gets very, very funny. So we'll talk about most of the prior work. I'm not giving you the details of all the papers, have been on how do we prevent congestion or how do we handle congestion. We had in a supercomputing conference last year a dynamic congestion management system. So there's a lot of noise in this area, a lot of work in this area, but we couldn't find any measurement studies. And we wondered whether congestion actually happens. So this machine, which is called Yellowstone, is run by NCAR. So John Dennis, my partner, has been using it for years. So he said, let's see if congestion is happening in Yellowstone. But the catch is they disable it. So the switches have functionality to recognize congestion and react to it, but the administrators don't like the way it operates, don't like how the parameters are set, and so they disable it. So if they disable it, how the heck do we know if it's happening or not? Right? So that was a head scratcher. So here's a bit of a motivation. So John Dennis is part of this giant team. In fact, his group was that they were part of the group that won the Nobel Peace Prize along with Al Gore a few years ago. John wasn't part of that, but there was a group at NCAR that did this work. So they have the simulations are just awesome. It's like the ocean and the land and the atmosphere. And so what this graph is showing is that there's a lot of variability, right? So you're getting a huge amount of variability in execution time at different runs. And the question is this happening because of OS jitter or network congestion? What OS jitter means is that the computing is doing other things, right? So in HPCs, you typically disable a lot of stuff like NTP and so on, but you still have some activities that occur which could be occurring at those runs but not occurring in these runs, and so you get a variation. So John was particularly interested in whether or not congestion is occurring. So here's a little background on InfiniBand. It's, like I said, this transmitter dare not send unless it receives credits from this receiver. So it sends these things called, oh, sorry, that should be flow control packet. I was pretty sleepy when I made these. Okay, flow control packet. And then when it says, okay, I have enough space, you send a packet. So it's literally hop by hop, right? And so they're doing everything they can to avoid packet loss, presumably because you don't want the good old TCP transmissions, retransmissions. But like I said, bad effects. So here's what happens with congestion control. So let's say this port is congested. So what is InfiniBand? The protocol standard has congestion control mechanisms built into it. Only it's not enabled. Okay, two different things. Standards, manufacturers, Mellanox has put it into their switches, but Yellowstone operators don't enable it. But let's see what the standard says. So if that port is congested, the switch has to declare congestion, then you get a forward explicit congestion notification. And this thing, it looks at it's sent, it's a header bit. And so for every flow that's causing congestion, the recipient is getting that marked packet. And so it causes this to send a backward congestion notification to the source, and the source then reduces its injection rate. And then you've got to unravel that, right? So as congestion dissipates, this thing goes away. Oh, I forgot to start my timer. Somebody give me a heads up. All right, I'm going rather slow. So that's congestion control, right? But this is what happens, how congestion spreads because of link-by-link flow control. So Fabrice made this slide. He was very excited with all the animation. Let's see if I can do this right. So a whole bunch of green packets. So there's a green flow going from here to there and from here to there. So you can guess that that's and from there to there and from there to there. So that's getting congested. So if this is getting congested, and these green flows are creating the congestion, this orange flow, yeah, Virginia's colors are orange and blue. So Virginia's flows shouldn't be affected, but indeed they get affected because this thing fills up, and so guess what? You get no credits, and so that this is called a victim port, and this then becomes a victim flow. So even though this flow is not traversing the congested port, the poor sucker is hit. Yeah, not a good idea. So it really makes you think. Donald Trump. Okay, so Yellowstone cluster. So this is what this looks like. It's a classical leaf and spine type structure. You have Tor switches, top of the rack switches. Each switch has 18 hosts on it. And this is called an A group. Together you got a B group, and you get a bunch of B groups, and they're connected by leaves and spines. Orca, turns out, is not an acronym, it's some Mellanox word. But importantly, this is the I/O system, disk I/O system. So hanging off of that is your file system, Lustre. They run GPFS, which are parallel file systems. And this is a data analysis and visualization tool. So we really expected, actually these are small clusters, so we expected all the congestion to happen there. Because when you're doing a large file transfer, that's when you're going to get packets at high rates. But it turns out that these links are congested. So you're going to hear me say up and down a lot. So up means that. The Tor up port is the port going up toward the tree. And this is the down port of the Tor switch. So down is this, up is that. For the leaf, this is down and that is up. And because the spine is at the top of the heap, it has no up. Okay? So that's the story. So now that I've set you up, so I'll tell you what we did with the measurement study. So it turns out, so you'll know about SNMP and Ethernet. So I do hang out in that IP Ethernet world most of the time. This is an aberration for my research portfolio, if you will. But it's been great fun learning a new protocol. And so just like the SNMP counters, here you have port XMIT conj time, congestion time, and port XMIT wait. So that's what those counters track, whether you're congested and whether you wait. But if you've disabled congestion, this is not going to register anything. It's going to be a good old goose egg, right? 0 all the time. And so we decided to observe this and said, okay, so it turns out that this is a conservative estimator, and I'll answer 3 questions that will explain why this methodology works. So first of all, how does a switch decide that a port is congested? When you get, I did a little animation last night, so you get a bunch of packets coming in like this. So there's this concept of virtual output queues, right? I don't know if you all know, but there's something called head-of-line blocking. So some of you might have switching hats. And so you don't want a packet to be stuck here because this port is congested. If the next packet behind the first one is headed toward 3, you want it to be able to get through, not to have head-of-line blocking. And so a typical input queuing switch design has something called virtual output queues on the input port side, on the inside. And so for each of the output ports 2, 3, and 4, you have a separate buffer. It's virtual, right? So this is one example of what one vendor wants to do or does. I don't even know if it's a vendor. It was a paper from a university in Sweden that said we would set this fill ratio to say 83%, and if that's at 83%, you declare that this port is congested. So note this buffer is not full, right? But so the question is, if port exit weight starts increasing, because this we can observe, because flow control credits are going to be denied, then does it necessarily mean that there's congestion downstream? And the answer is yes. So let's say I have a flow going there, and so if all these packets are headed towards that port, and they all come in and fill this up, if this port exit weight starts increasing, it means there were no credits. It necessarily means this was full. It necessarily means that 83% was exceeded, and so there is a downstream port that was congested. So that's the logic. And so on the flip side is not true, right? So if, let's say I'd made my L was an 83%, I got tired of making these brown thingies. So I said 50%, so it's half full. And so switch B declares this port to be congested, but you're not going to get any flow control, a lack of flow control credits. You're still going to get 3 credits, right? Credits for 3 spaces, so your port exit weight is not going to increase. So in other words, if we look at port exit weight and say that's going up, it means somewhere downstream there's a port that was congested, right? And so all we needed to do was to show the Yellowstone administrators that, gee whiz, there's definitely at least this much congestion. You better get your act together, right? So that's sort of what we tried to do. So InfiniBand has a software called OFED. It stands for something. Open Fabrics Enterprise Distribution. I didn't bother to put that more jargon in there. But it has a bunch of really cool utilities, kind of like the pings and the trace routes that we're used to. So you can read port counters using perf query. You can sort of go through with this IP. There's a diagnet and a net discover to figure out the topology. So Fabrice, my student who graduated with a master's in 2016, he wrote all of the script, ran the script, collected 30 million records, not a huge data set, but we were using compute cycles. It was a lot of compute cycles we kept using, so we were running out of cycles. But if you're interested, here's the data set. So you have to ask for compute cycles on Yellowstone. So if you want the public data set, you can look at it. So we defined this thing called a round. So we pick a port, right? The script picks one of those, I don't know, tons of ports, right? There were each of the Tor switches has 36 ports, and there were about 250 Tor switches. So lots and lots of ports. So we arbitrarily pick a port, stick with that port, and query it 100 times. And the times between the queries are 10 milliseconds. So we hang with that one port for 10 seconds. Okay? And so so that's called a round. So at the end of that 23 days, we had, for example, we had queried Tor down ports. You remember what I said? Tor down port goes toward the host 60,000 times approximately, right? And so if the port expect wait, the way it works is it increases by 22 for 22 nanoseconds. If I don't get a flow control credit, I'm going to increase that counter by 1. So you multiply that out, divided by the number of the times between the reads. But we're running these utilities on a computer, and it has to, the message you're sending has to wend its way through the fabric, right? And so there's a delay between what we are timestamping at the server and when the query actually gets to the switch. So we get some funny results because of that. And so the time is at the server, not at the switch where the query is being issued. So here are a couple of examples. So this is a Tor switch. It was one of the down ports going downward. And what we found that, like you see here, on this query, like the value was here, the next query jumped up, right? That means during that 100 millisecond period, there was a denial of flow control credits. That means some port downstream was congested. But then it didn't increase for a long time. That means there was no congestion for any of the ports downstream of the port that's being queried. So this is beautiful, and we'd like to see more of this, but instead we saw a lot of that. For every time we went to query, the port expect wait had grown. That means that there was a denial of credits. Yeah? And so, what we did was we had three questions really. How often do these events occur? How long are they? And how bad are the really bad ones? So John was interested really in this frequency, and I'll explain why. So we took all this what we call FITF, the fraction of idle time, forced idle time fraction. You're forced because the other guy is not willing to take my packets, right? Say 6 million. How many of those, what percentage of those were bad? So we were really surprised in two ways. First of all, we found that like with the Tor downlink, we had queried those 6 million times, and we found 60% of the observations of those 100 millisecond intervals, the port had been shut down for a lack of credit. That's huge. That's really a lot of times when that port is being told not to send packets. Mind you, you know about buffer bloat in the internet? This is just the opposite. The buffer sizes here are, I want to say 32 MTUs, and 1 MTU is 2 kilobytes. They're really small. Okay, so they were forced to wait for credit 60% of the time. The other unexpected part was we expected. Remember I talked about that disk I/O system called Glade and this data analysis and visualization system? Well, no, the action was actually more in the Tor switches. So this corresponds to Tor, up and down, right, or the other way around. And so we were surprised by the frequency. Now, how long were these? So what we did was my student, Fatma, she took out all the 0 rounds, so the box plots would be a little prettier, visualize better. And so you can see here, first of all, before we get to the Glade, that the maximum, let's look at this maximum fraction, is 10%. So out of 100 millisecond, at most, where we took the outliers out, at most it was about, out of 100 milliseconds, 10 milliseconds when the port didn't get to send. Now 10 milliseconds is really an aeon, right? It's astronomically large because we're talking about very high-speed CPUs operating, and with lots of parallel stuff, nanosecond speed. So 10 milliseconds is a giant wait. Okay, so this is, so you can see that there is 4 millisecond delays and so on. But the Glade, as we expected, had the most variability because that's where you're doing all the large. When you're sending a bulk data transfer, it's more likely that you're going to see some congestion. So what are the worst case values that we saw? This is a bit of an eye chart. So we said, we'll get to this in a minute. There were some intervals for the entire 100 millisecond when the port was shut out, right? And so those fell under the outliers. We took them out of the previous picture. So to give you an example, we saw about 3,000 outliers within the number of rounds that we queried a tore down switch, right? Now you see some fractions that are greater than 1, so how impossible is that, right? And the reason that's possible is because of this timestamp issue. So we're timestamping at the server, and then we are dividing that round trip by 2. But if the previous query had gotten there in a hurry, and the next query took its own sweet time, or the other way around, you could end up where the actual time that the switch port gets queried is less than 100 milliseconds. And so that's why you end up with this slightly greater than 1. But greater than 1 just means that the port was shut down the entire time. Okay, so that's that. So what's the impact of these findings, right? So this is actually sort of an old paper from 2003, and it wasn't done in the context of InfiniBand, but in the context of just supercomputing applications. That what they found was a lot of these climate applications, I don't know if you'll have done MPI coding, but you run a bunch of MPI tasks in parallel, and then you hit these barrier calls, or wait all. You need to synchronize all the tasks before you move on. And so in those types of applications, where the messages are really small. So Fabrice ran this, it was a simplified version of Home. We just ran it with 90 cores. And John Dennis and the professionals tell us that it's not worth running unless you use at least 1,000 cores, because otherwise it takes longer to simulate 1 day of climate than 1 day, right? And so it's catch-22, you can never catch up. And so we just did a 90 core run, and this one synchronization call was called 140,000 times. So you can just imagine if one message gets delayed, all the tasks are held up. So this increases your execution time. Yeah, one task got delayed. So the communication, the message, it's trying to send the neighbors. So the way they simulate, they divide Earth into, I don't know, sectors. They put something around the globe. So each node has 8 neighbors. And all the computation that it does, it has to send some data to each of the neighbors and get responses back before it can proceed. And so your execution time is affected, but also your CPU utilization. I don't know if you walked into any of these HPC centers, like at NERSC in Berkeley and stuff. If you go and look, you'll see they're very, very proud of their HPC systems being 99% full. And so every time these computers are these cores are just sitting there doing nothing, waiting for communications, it's bad. So I really feel as a network engineer, I had something worthwhile to offer. So I do think our measurements, we've sent this paper to a bunch of guys who run machines like Yellowstone and said, hey, y'all better enable congestion control. So to just the last slide, pretty much repeating what I said from the previous slide, we were very surprised that the Tor ports were suffering congestion. And this is why I had to give you this little song and dance about how the congestion effects spread. So the congestion may be starting in Glade, right, in the Glade subsystem where you're doing disk I/O, but it's coming back all the way to the Tors, and so most of the computation is called IPC. So there are 3 types of communications in these HPCs. You have inter-process communications, you have communications into disk, usually that's fiber channel, and you have, so InfiniBand for IPC, you have fiber channel for going to disk, and then for wide area, you have TCP/IP over Ethernet. So most of these HPC systems will have one node, one computer, or actually a small cluster that has Ethernet on one side and InfiniBand on the other side. So for this communications, you're going to suffer quite a bit. So some of them really lasted a long time. We are pretty confident that our methodology makes sense. And so either they should enable congestion control and use our dynamic congestion management system, or some other system if you have trouble believing how the thing is, to do congestion control, there are a lot of parameters. You have to set something called a switch marking rate for all the switches. And then in the host, you have to set a parameter that controls how rapidly you decrease the packet injection rate and how rapidly you increase it back. So people are nervous in this community about not knowing how to set those parameters right. But either they have to do that, or they have to change applications to leverage, just like Ethernet has VLANs, right? To isolate packets. You want to isolate applications that generate these short messages from the long bulk data. So that's our story. Thank you very much for listening.
Questions?
Yeah, so probably first question, do you guys have a separate dedicated air-gapped out-of-band network from which you would be doing the measurements? Or you use the in-band network? So you technically saw your own measurement packets on your results?
Right, but it's very light relative to how big the network was, right? And it's only 20 minutes, yeah? Other questions? It's a good one, a good question.
So, if I'm not mistaken, also Ethernet is a pause mechanism to stop the sender to avoid overflowing the buffer, the upstream switch and so on. Do you think some of this may apply also for Ethernet switches? It's even more critical because there it's 0-1, you're taking credits and so on, right?
That's right. Yeah, so ever since GigE, we have that pause feature. But most switches, most administrators do not enable that. But if you build, so in the world of cloud computing, I heard a really good talk by Jeffrey Fox, I think, from IU. He talked about the world of ABDS, Apache Big Data Systems, which is all the commercial clouds and HPCs. And so the commercial cloud data centers all have Ethernet-based switching. They have these factory structures, but they're Ethernet-based. So there's something called RoCE, RDMA over converged Ethernet, to bring the InfiniBand transport protocol to run on top of Ethernet. I think it's a really bad idea, but they're trying that, so that is there. Thank you. All right.
Any other question? I have a question.
Oh.
Are there any report or measurements proving that actually congestion control, when you enable congestion control, things are going really bad? I mean, about those times.
Good question, but not on a large scale. And so this world is dominated by one company called Mellanox. Yeah. And so Mellanox and IBM together wrote a guide saying don't enable congestion control, even though the standard has it. And then a bunch of profs. There's a group in Sweden, another group in Germany, who all worked on showing on a baby test bed. You enable congestion control and you can set the parameters well. So there have been papers especially from 2010, there have been a lot of papers in supercomputing showing that. So we researchers think you can do it, but the administrators don't believe us. So there is a gap there. Yeah? Okay, thank you.
Any other questions?
Nope. Break time.
Okay, not let's thank again Malathi.